Okay, good afternoon, everyone. So this is the lab for week 5, and the topic is interpolation. So first, you have to download the file called dd.m. So this one is the file that you can see it in the directory for week 5 lab, or in the lecture notes, in the interpolation topic. And so I just downloaded and I put in my MATLAB directory, and I can share my MATLAB screen. So this is my MATLAB screen, yeah. So just cleared, and you can see that I put dd in the directory already. So if I want to see what is inside dd, I just type dd.m. Okay, and you can see that dd just computer divided difference table. Suppose you supply two vectors, x data and y data. So x data is like x1, x2, x3, okay? And y data is fx1, fx2, and fx3. And then it just compute the divided difference table for you according to this formula. Okay, remember, I did it by hand in the lectures already. Suppose you want to compute this for, divided difference coefficient for x1 and x2, then you just take the difference of fx2 minus fx1 divided x2 minus x1. Okay, and so on. So this is the implementation, and now we will use it for our problem. So now suppose I make a new script. Okay, so my new script look like this, and if you see the problem, so the problem is we have to put in the data first, yeah. So the data is, so if you see the data is right here. So the data is, yeah, the data is here. So x is 2.0 and increase by 0.25 and stop at 3, yeah. And so what is the y data? So the y data is the values of the Bessel y function. Okay, so you can look up what Bessel function is, but essentially, when you try to model the wave, say, suppose the mobile phone tower, right? So suppose the radio wave emit from the tower, then you can model the wave by this Bessel function. Okay, but now we just use the Bessel function, and we will try to construct the polynomial that approximate that function. Yeah, so first I will define the vector x. So I stop the I will share the MATLAB. I stop the question. Yeah, so first I will define x data. So x data will be, you start from, you start from 2, yeah, and you increase by 0.25 and you stop at 3. Okay, so this is my x data. Okay, and what is my y data? So my y data is, remember, it's just a Bessel function y, Bessel function y and order 1, right? And I apply to the x data point. Okay, so now I run it. So if you see that I can run this, yeah. So I have to give some name. So I give a name, say week 5 question 1, yeah. And you see, if I run it, then you can see that x data is this number 2 2.25, 2.5, 2.75 to 3, yeah. And the Y data, so this one is the somebody asking something. Let me see whether I have a question in the chat box, or yeah, somebody asked me something. Yeah, okay. So what is best of Y? So best of Y is the built-in function, okay, in MATLAB that compute the Bessel function for you. Yeah. So Bessel function of the second kind. So first, so I explained to you already. So Bessel function is so Bessel is the name of a German mathematician. Okay, and he discovered this function like a few hundred years ago. Okay. Okay. So what is one? Okay, one is the order. Okay, because like yeah, here Bessel Y. Yeah, you can see that. So new is the order. So here we have Y1. So it's meant that order 1. So that's why I put 1 here. Yeah. Okay. So got it right. So now, so now you can see that if I put in Y data, okay, then you can see that is identical to the column in the question. Yeah. So it exactly what it is in the right columns of the question. Yeah. Well, maybe only the last few digits are different, but because this function, you know, we have no exact formula, so there's some approximation. Okay, but this function is very important. Okay, because suppose you try to model say radio wave from a tower, from a cell phone tower, then you have to use this special function. Okay. Okay, so but now we got on the data, and now let's construct a divided difference table. So now I construct a divided difference table. So construct the divided difference table. So I got T will be DD divided difference table X data, comma Y data. Okay. And now you can run it. If I run it, yeah, then you can see that this is my divided difference table. So maybe let's make it easier to read. So I have maybe format short. Okay, so you can see that this table is right here. Yeah. So on the first column, just the X data. And then the second columns is my Y data. And this one is a divided coefficient. Divided coefficient is computed. Yeah. So that is number 2. And now construct a Newton form of degree 4. So construct Newton form of degree 4. Yeah, that interpolate the data. Okay, so the formula, okay, so now first I write down the math formula. Okay, so P4X will be Fx, how do we say that? X1, oh no, sorry, X0. Okay, plus the divided difference of X0, X1, X minus X0, plus, okay, divided difference X0, comma X1, comma X2, X minus X0 time X minus X1, yeah, and so on. Okay, so when do I stop? So, well, because my polynomial is degree 4, right? And I have only quadratic terms, so I need to move on. So I have to put in the next term is the cubic. Okay, so this is my cubic. So am I done yet? No, because this one I have only cubic terms, yeah, but I need a degree 4, right? So I have to put in one extra term. So what is you know, I mean the divided difference over x0 up to x4, and the product we have x minus x0, x minus x1, x minus x2, and x minus x3. Okay, so that is the, so this one should be x2, yeah. So that is the full polynomial of degree 4 that interpolates the function Bessel y, okay, over the data points. But now the question is, how do I convert this formula into MATLAB? So how do I convert this into MATLAB? Well, okay, so now I define P4 as anonymous function. Okay. And first, where do I get the divided difference coefficient? So where do I get the coefficient? So where do I get the divided coefficient, divided difference coefficient? Fx0, Fx0, x1. The second column. Well, the second column of the table is the x data. Well, what is, I mean, at least it's correct for the first term, yeah. So the first term is, I will type in like my table and row 1, column 2, right? So this one is my fx0, yeah. And now where do I get the next coefficient here? So where do I get this? Where do I get this fx0, x1? Yes, row 1 again, yes, agree, but in the next column, yeah. So then you have, so this one, now you can use the divided difference table, yeah. So this one will be my row 1, column 3, yeah. And now I have to multiply with x minus x0. So what is my x0? So x0 is just the first data point, okay. And because MATLAB doesn't allow you to have a 0 index, so you have to start at 1. So this one is just x0, just the first point of my data, x data, yeah. And then I have, no, this one is just a linear term. Now then I move on to the next term, yeah. So this one, then I have to take T1 comma 4, and then I have to multiply by x minus x data 1, x minus x data 2. Okay, so now I have to got into a new line because it's a bit too long. So I got T1 5, okay, and then I have to multiply by 3 terms, remember? So we have 1 terms, 2 terms, and now 3 terms, yeah. So copy and paste, and this one is x minus x data 3, okay, and then T1 6, and so on. So T1 6 is the last coefficient. Okay, and do not forget to multiply by the last, well, not the last, but near last, yeah. So, and actually I should have only 1 star here instead of 2 star. Okay. And that's it. That's it. That is, no, this one is the 1,6, yeah. Okay. And if you want to take in vectors, then you can put the dot here. Yeah, so x could be a vectors. So instead of a single number, x put a vectors, then you just put a dot. Okay, so that is my before. So this is my before, right? So now the next one is now you construct polynomial P3. Yeah. So construct P3. So this one is a cubic. Okay, so construct Newton form of P3, yeah, of a cubic of degree 4 polynomial. Yeah. So now of a cubic that interpolates at x1 equal to 125 and so on up to x4 equal 3. So what is so special about this P3? So what is so special about this P3? So I mean, if you look at the point set, yeah, the point set is just the last 4 points. Okay, so it will be the last 4 points here. Yeah, so before you have 5 points, yeah, start from 2, ends at 3. But now it start at 2.25, okay, and increase by 0.25 and ends at 3. Yeah. So there's 2 ways. You can reuse this table, or you can extract, you know, a subset of X data and Y data, and you construct another table. Okay, it's up to you. Yeah. Let's suppose I don't want to construct a new table. Then how do I get the coefficient for P3? Okay, so maybe before, yeah, just use row 2. Yeah, so if you use row 2, then you get the coefficient here. Yeah, so if you use row 2, okay, then you have, so now I use row 2. Yeah, so T row 2, and then so that's the first data point, and then I have the row 2 3 multiply with x minus, now we have to be careful. So x data, we cannot take the first data point, right? Remember, we start at the second data point. So I have to start at x data 2. Okay. Yeah, so it's a bit dense here, yeah, but maybe make it look nicer so you have easier to read. Yeah. Okay, so we got to start with x data 2, right? And now the next one will be t to 4, right? And you multiply with x minus x data 2, x minus x data 3. Okay, and then t to 5. And now just cut and paste. Okay, so x minus x data 4. That's it, because this is a cubic. Yeah. So I stop here, stop at the last term. Yeah, the last term is a cubic. Okay, so start with a constant, linear, quadratic, and cubic, and stop. Yeah. And now we have to use P3 and P4. So use P3 and P4 to estimate the value Y1 at 2.6. Okay. So now let me call 0. Suppose I call X0 is 2.6. Yeah. So the point I'm interested in. Yeah. Then what is the approximation? So approximation will be so approximation say 1, yeah, will be P3 at X0, right? I just evaluate the polynomial at the point I want, right? And approximate 2 will be P4 at X0, yeah? But what is the exact value? So I want to approximate this value, right? So what is the exact value? So what is the exact value? And now after I got, yeah, exactly. So it's just a base of Y 1, 2.6 and 2.6 is X0, yeah. So we just give it X0. So if we want to replace X0 by something else, then we make it like this. Okay, so now print out the errors. So now print out the errors. So print out the errors. So F print F, then errors in the approximation, then F print F. Now you write out P3 X0. So I want to write X0, but you know, I just put in some real number, right? So because I want to suppose I want to change the value of X0, yeah. So what is the value I want to print out? So the value I want to print out is X0, X0, and then the errors. So the errors will be, well, another number here, yeah. So another floating point here, and I will put absolute value of approximation 1 minus exact, yeah. And I can do the same for the second one. Okay, so this one will be P4. Okay, then approximation 2, right? Okay, and now let me run it. So if I run it, something wrong. So line 12, column 71, line 12, column 71. We missed the close parenthesis, yeah. We missed the close parenthesis here. Maybe it will fix it. So no, miss it here as well. Okay. That's it. So now run again. Okay, so I run again, see? So maybe now I don't want to have a lot of digits after the dot, that I put, say, maybe 2.4 after the dot. So 2.4, 2.4, 2.4, and maybe this one I want a bit longer. So 1 point, so how many? So maybe 10, 1, 10, and then I run it again. You see, so I have a little bit nicer, yeah. And you can see that P4 has a smaller errors than P3, right? And you can change this one to say 2.76, and you run it again. So you got another errors, yeah. And now suppose I want to plot it. I want to plot the well, maybe plotting is the next question. So, but you can plot it, yeah. Suppose you want to plot it, then you can plot by the following command. So suppose I put in say 2 to 3, put in 10,000 points, yeah. Then I just plot x plot, okay, so y 1 x plot, maybe in the blue color, yeah, and then x plot p3 x plot in the say red color, yeah, and then x plot p4 x plot in the magenta color, yeah. Now I plot it, so not suppose I plot it, and no, something wrong. Okay, so we have to make everything is compatible to vector, so you have to put a lot of dots. So put a lot of dots here, yeah, in front of the star. Okay, and then run it again. Okay, so you see the plot. Maybe not. Let me share the screen. So maybe this one is maybe to 5, yeah. So if I run it, yeah. And let me share the plot. I share you the plot and you can see it. So this is the plot. So you can see it. So the exact function is the blue one, yeah. This is the exact function, the blue one. And the red one is the P4. Okay, so P3, sorry, P3, yeah. And the magenta is P4. You see, so from 2 to 3, it seems that they agree very well, yeah. So the error is very small. But if you go a bit further, yeah, so then the errors now become bigger and bigger. So it seems that interpolation works well only on the intervals that we supply the points, yeah. Remember, we supply the points, you know, x data from 2 to 3. Then it fits very well. But outside that range, then it's a problem. So the more data point you give, the better the approximation. Okay. So any question for that? Okay, so otherwise, if there's no question, then we move to the next question. So the next question is, so we got the first question done, yeah. And now the next question, I think this one we can skip because it just compute the divided difference. Okay. But the third question is exactly the same, but you just replace the function f by tan inverse. Yeah. And you replace the data point is 5 equally spaced point from -5 to 5. Yeah. And then we plot it from -pi to 2 pi. Yeah. So you can copy and paste exactly the same solution for the first question. Yeah. So let me make it exactly like this, and we can make the second question. Yeah. So now I got the whole thing here. Okay, I got, and then I copy to the next one. Okay, so Now remember what is the function. So the function is just tan inverse tan, yeah, tan inverse tan of x data. Okay. And what is x data? So x data just a length space from minus pi to pi, 5 points. Okay. And now we need only P4, so we don't need this. We don't need this. Get rid of this one. Yeah. And then now we need to plot. Okay. So now the plot is just the well, the range will be from minus 2 pi to plus 2 pi. Okay. And now we need to plot only the arctan function. So arctan of this in of x plot in blue. Okay. And we don't need P3 anymore, right? So we just need P4. Okay, and red. Yeah. And then that's it. So we just cut and paste exactly the same thing from the previous question. Okay, so we just reuse the previous command. And now, so this one is make a plot, yeah. And now let me run it. So we have to save it first. So I save it. Week 5, question 3. Okay, so I can share to you the the graph. Yeah, so let me share. I'll stop this first and then share the output. So you can see it. So the blue one is the arctan function, yeah. And the red one is the interpolation, and you see that they agree very well in the range that you provide the data, but outside that range, and the error is very big. Okay. And we didn't plot the point, so we can plot the point. Yeah. So let me plot the point for you. So how do I plot the data point? So I can plot the data point by maybe by typing this command. Yeah, hold on. This means that I want the figure is still there. Then I plot x data, y data, and just the markers. Yeah, the big one. And now let me run it to see what is the output. So maybe grid on as well. So make a grid. So now what is my output? So let me have a look at my output. So there's some question. So hold on. Okay, what does it mean? So hold on, it means like you don't want to erase the plot. You don't want to close the plot. Yeah, but you want to plot another plot on top of it. Yeah, so this one, yeah. So hold on, it just means that you don't want this plot disappear, right? So because I want to plot the data point on top of it. Yeah, so hold on is like you just keep the figures on. You don't want to close it, and you plot on top of it. Yeah. So let me show you the output. So where is the output? So you can see the output look like this. So remember before we plot two curves, yeah? Okay, and I say hold on, then the figure is still unchanged. Then I plot the data point. So you see that now there's an extra 5 data points, yeah? So the hold on command, keep the figure still on. So then I can plot something else on it. That's it. Otherwise, it will create another figures. I don't want that. I want to plot the data point on it. Yeah. So that's it. So close. And now we go back to the question. So now what is the next question? Okay, so the next question is interesting. So it's inverse interpolation. So inverse interpolation. So what does it mean? So first, there's two Newton. First is the Bessel function J. Okay, so before we have a Bessel function J. No, so before we have a Bessel function Y. Yeah, and now we have a Bessel function J. So it's just another family of Bessel function. Yeah, but what do we want to do with this? Well, we want to find the zero. We want to find the roots of this function. Okay, and how do we do that? We will use inverse interpolation. Yeah, so let me explain to you by pictures. Yeah, so maybe first okay, so we can close this. Yeah, so close. Okay, so maybe new script. Yeah, so maybe let me plot the function for you first. Yeah, so lin space from 2 to say 4 and 10,000 points. Yeah, then I want to plot x plot Bessel J order 0 x plot. Okay, so now if I run it, you will see that. Okay, so this is week 5 question 4 and grid on. So make a grid on this. So now let me share the pictures. Yeah, so I want to share the pictures, the output. Okay, so if you look at this, so this one is the Bessel function J of order 0, right? And it's going down, yeah? And it will cut all x-axis here at this point, okay? And the question is, I want to find this 0. I want to find this point. I want to find the roots of the function J0, okay? Well, approximately, yeah? So how do I do that? So now I'm going back to this, yeah? So I want to find, so I want to find P star, right? So that J0 P star equals 0. Okay, so that is what I want to find. And what does it mean here? So now P star, I mean, if J0 P star equals 0, it means that P star is J0 inverse of 0, right? Okay. And now, how do I find J0 inverse? Well, I don't know, right? I don't know, but I can try to approximate J0 inverse, okay, by a polynomial. Yeah. And you see, because J is a function of X, yeah. So therefore J inverse is a function of Y, okay. So therefore P3 has to be a function of Y, yeah. So now how do I find P3Y? Well, I mean, so this one is a function of Y, yeah. Well, how do I find the function P3Y? Well, so remember the interpolation condition. So now you have X1 and you have Y1, right? So you have Y1 equal something, right? And you have Y2 and X2, right? So what is the relation between X1 and Y1? Well, remember X1 is just J0 inverse of Y1, right? Because Y1 is just J of X1, right? So another word is X1 is just J0 inverse of Y1. And similarly here you have J0 inverse of Y2 and so on. You know, so I have 4 points. So I just cut and paste this one, yeah. And I have 3, 4 here. And this one is 3, 4. So you get the idea, right? So, but now what is this one? So this one is the divided. You can construct a divided difference table based on this, yeah. Because you see this is a function of Y, right? And it satisfies the interpolation condition. So you can construct a divided difference table exactly like before. But the difference is you have to swap the rows of X data and Y data. Yeah. So now I will do something like this. I will have X data, okay, will be 2.2. Well, it's given as the table that in the question. So stop at 2.8. Okay, so this one is given. And then I have Y data. So Y data is just like before, Besso J order 0 of X data. Okay, so I have, so far I have exactly like before, right? So now what is the next step? So what is the divided difference table? So how do I call DD to compute my divided difference table? Well, I have to swap the row of Y and X, yeah. So you see it. So now if I run it, what do I have? I will have a table like this, okay. And you can see that the first columns is just the Y data points, yeah. And now this is the X data point, yeah. But the X is just a value of J inverse of Y, yeah. So therefore, this coefficient will give you the coefficient of P3 of Y. Okay. Yeah. So now how do I write out P3? So I will write out at least in terms of mathematics first. Yes, I will write out P3 is Y1. Oh, not Y1. Sorry, not Y1. Should be J inverse of Y1. Yeah, where it's just X1. Yeah, yeah, because you swap the row of X and Y, right? And then now I got a divided difference table. So now maybe let call G, yeah, to be J0 inverse. Otherwise we we have to write this again and again, yeah. So I will write out G of divide difference over y1, y2, yeah. X minus, no, now it's not, cannot be X, Y minus y1, okay. And then I have G of y1, y2, y3 of y minus y1, y minus y2, right? And the last term is G of y1, y2, y3, y4, y, I mean, I just cut and paste this one, and then I multiply with y minus y3, yeah. So you see the construction, right? And so now remember P3 is a function of y, yeah. So now I will do exactly like this. So P3 is a function of y, yeah. And the first one is just x1, so x data 1, okay. And now, or you know, I mean, it could be as the second. We can write it, or we can write as a second column, first row of the table T, yeah. Okay, like we did before. And then we have T1, 3 multiply with y minus y data 1, and then plus T1 comma 4 y minus y data 1, y minus y data 2, dot. So I want to have a new T5, so 1 T comma 5, yeah. And I have to give this term, so y minus y data 3. Okay, so this is my P3, okay. And now, so I construct a polynomial. So this one is my x equal P3. No, maybe construct P3y, yeah. That approximate, that interpolate, yeah, interpolate G, okay. What is J0 inverse? J0 inverse. Okay, so I got it. And now, how do I compute P star? So what is my P star? So what is my P star? So how do I compute P star? So how do I compute P star? Yeah. Yeah, so just P30, yes, correct. Yeah. So you still paying attention, yeah. So you just put P star is P3 at 0. That's it. And you know, I mean, you can evaluate what is J0 of P star, right? So maybe you print out. Okay, so maybe this one is you print out, yeah. So f print f P star equal something here, P star, and F print F. So now you want to print out J0 of P star equal something, and this one is special J0 P star. Okay. And I forgot to close the sentence. So now if I run it, so you see that my P star is about 2.4 something, right? And G0 P star is very close to 0, you know, just like 10 to the minus 6, yeah. So, and if you compare with the plot, so remember we have a plot before. So I close the plot, but now if I have the plot again. So I stop this, I share the plot. So you see that we found out that P star has to be around 2.4 something. And you see 2.4 is right here. So 2.4 is exactly when it cut the OX line. Okay, so this is the way you find the zeros of a function. What is the topic for tomorrow lectures? Okay. So any question? So that is the lab for today. So any question? So let me share the commands again. Yeah, so this is like you construct the divided difference table and you define P3, you compute P star. Okay. So why P star is P30? Okay, it's good question. So P star, you remember, okay, so that is exactly what I try to explain here. So we want to find P star, so that J0 at P star equals 0, right? Yeah. And then it means that P star is J0 inverse of 0, right? And we approximate J0 inverse by P3. Okay. So after we got P3, we have to put in 0 to approximate J0 inverse of 0. Okay.